Okay, so what we want to now prove is uh, some of the properties of the minimum spanning tree with regards to having unique edge weights or not having unique edge weights. So the first thing is quite easy. So if you have a graph that does not have unique edge weights, which means it could be a graph like this where more than one edge has the same weight. So this edge has weight 1, this edge has weight 1, this has 2, and this has 2. So this graph does not have unique edge weights. So if you have a graph that does not have unique edge weights, then there could be more than one minimum spanning tree for the graph. It means it's not always the case, but there could be the more than one minimum spanning tree for the graph. So for example, if I pick these two ones and just pick this two, it could be this minimum spanning tree. If I pick this two instead of this one, it could be this minimum spanning tree. So it could be two different minimum spanning trees. So, but still the sum of all the edge weights is the same. So this is 4 and this is 4, right? So that should be maintained. So the total weight of all the edges that form the minimum spanning tree should be the same even though you have more than one minimum spanning tree. Okay, so this is a proof by example where you just come up with a small graph like this, and that does not have unique edge weights, and you can show that it is possible to have more than one minimum spanning tree. Now, the next property you're going to look at is if a graph has unique edge weights, then what we want to prove is there can be only one minimum spanning tree for that graph. So how are we going to prove that? It's a proof by contradiction technique. Um, let's say that there are two different minimal spanning trees for that graph. So let's say the minimal spanning trees are T and T prime. There are two different minimum spanning trees, which means, like I just said, the sum of edge weights should be still the same, which is the weight of T has to be equal to the weight of T prime, let's say like this, but they have different sets of edges because what we are telling, there are two different minimum spanning trees. Now also remember the graph has unique edge weights, so which means no two edges have the same edge weight. Okay, so given that the graph has unique edge weights, assume that there are two different minimum spanning trees T and T prime. Since there are two different minimum spanning trees, there has to be at least one edge difference. So which means there should be an edge E which is in T, not in T prime, and there should be an edge E prime that is in T prime and not in T. So like we did in the previous proofs for the correctness of Kruskal's algorithm, if we put this edge E in T prime, it's going to create a cycle, right? So, or put this edge E prime in E as I show here. If I put this edge E prime in T, it's going to create a cycle like this. Now, now we want to decide which among these two edges have a smaller weight. If the weight of E is less than the weight of E prime, if the weight of E is less than the weight of E prime, then I could, as I just said, put E here and remove E prime, right? Like this. I could put E here and remove E prime. That would be still a spanning minimum, first of all, it's a spanning tree. But if weight of E is less than the weight of E prime, T prime is no longer a minimal spanning tree to start with. Why? Because by doing this edge change, by removing E prime and adding E, I am able to reduce the weight of T prime because weight of E is less than the weight of E prime, right? So the modified T prime has a lower weight than this T prime, which makes T prime not a minimal spanning tree to start with. That's a contradiction, right? So if we want to maintain T prime as a minimum spanning tree, then the weight of E has to be greater than the weight of E prime, right? Because remember again that edges don't have the same weight. All edges have unique weights. So the weight of E cannot be equal to the weight of E prime. So if this, the first thing is ruled out, because if you want to maintain T prime as a minimal spanning tree, then if you go with the second one, the weight of E is greater than the weight of E prime like this, then I could as well retain E prime and remove E from T, making T no longer a minimal spanning tree to start with. But again a contradiction where we assume that T and T prime are minimal spanning trees. So if that's the case, then if you want to compare the edge weights, we cannot say weight of E is less than the weight of E prime. We cannot say weight of E is greater than the weight of E prime. So the only scenario is the weight of E has to be equal to the weight of E prime. Then only both T and T prime could be minimal spanning trees. It's just that both have the same weight, so instead of this edge we have this edge here, and instead of this edge we have this edge here, right? So that the sum of all the other edge weights plus this edge should be equal to the sum of all the other edge weights plus this edge. Okay, if you want to maintain both T and T prime as minimal spanning trees, then the weight of E has to be equal to the weight of E prime. But again, that's a contradiction because our assumption is what? The graph has unique edge weights. So if a graph has to have unique edge weights, then there can be only one minimal spanning tree for that graph. If there is more than one minimal spanning tree for that graph, then there should be some edge pair like this, that E and E prime, E in T, not in T prime, likewise E prime in T prime and not in T, such that the weight of E has to be equal to the weight of E prime, which cannot be the case if the graph has unique edge weights, right? So this goes on to prove that if no two edges in a graph has the same weight, then the graph can have only one minimum spanning tree. Okay, so we'll stop with this.